Today we're going to talk about a generalization of hard margin SVMs, known as soft margin SVMs, of course. So this is going to assume that you're familiar with hard margin SVM, so please make sure you watched the previous lecture carefully. Okay, so let's recall kind of what the picture that maybe you have in your head with hard margin SVMs looks like. So the picture you might have is something like this. Then you had these margins, which are kind of spaced apart from it, like this. And then you had points which lie on the appropriate side of it. So maybe some points lying on the margin, and then things which are further than that. And then things here, 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 and then things further than it, like that. So importantly, there's no points which appear within this margin. If not, then we'd have a different solution, which is like scaled, and the lines would be moved. But we don't have anything that lies within this margin. And most certainly, what we don't have is that we don't have points like that which lie on the opposite side of the hyperplane. And the data set is definitely linearly separable. If it weren't linearly separable, then there would be no hard margin SVM solution. So in particular, this can lead to some undesirable drawbacks. Let's draw a few cases. For example, like one drawback would be, suppose we have a data set which looks kind of like this for the negative points, and maybe something like this, and you have maybe more points over here. So in this case, this would not be solvable with a hard margin SVM because it is not linearly separable. You can't draw any line which will separate the blues from the oranges, and this is no good. So this is bad for hard margin SVM. So that's one drawback. We can't solve problems like that, and in fact, almost all problems are going to be like that in the sense that linear separability is kind of a rarity for problems of this sort. Another undesirable quality is the fact that suppose we had a problem like this, where we had maybe a lot of points which look maybe over here, and then we had some points which are over here. So that's nice because it's very well separated. Would find something in the middle over here, but what if we just had one point way over here? Well, then the let me even draw it more extreme. 1 point over here. Well, in this case, then our resulting SVM solution would be something like this, which is not that desirable because maybe you'll still think, okay, maybe there's just an outlier or something that went wrong, and actually a better hyperplane separating would be something like this. That would be much more desirable. So these two cases kind of are the maybe prototypical cases of why hard margin SVM doesn't work so great, just because it really requires that every point is correctly classified by the separating hyperplane. So instead, what we might want, or what we might try to do, is to in fact have relax that restriction a bit and not require that each point is correctly classified, but instead of requiring that each point is correctly classified, you pay some cost when things are not correctly classified, and you pay more depending on the more that you're wrong. So let's get more mathematical now. So let's recall what the hard margin SVM is. And the names hard and soft margin might be kind of clear at this point, where hard says like it's a hard margin, you can't go beyond it with a point. But a soft margin will allow points to go over that margin. So recalling, we have min over w comma b. You do this, 2 squared, 1/2 maybe, and such that we know for all points, let me yi times is greater than or equal to 1. Now let me just recall some notation I introduced, but didn't use too much. We'll use it more in this lecture, where this is going to be yi hat. This is kind of equivalent to saying, another way of rewriting this is that we want that 1 minus yi hat is going to be less than or equal to 0 for all I. So this is another way of writing the constraint. Okay, and you can see that just by moving this over to the opposite side, and it'll be 0 is greater than or equal to 1 minus yi hat. Cool, so this is the hard margin SVM. So now what we're going to do is we are actually going to replace these constraints. So yeah, this is just going to be these constraints for all I. What we're going to do is replace this so that we try to encourage these to be less than or equal to 0. But if not, that's okay, and we'll pay something for it. So let me write it here, and then we'll kind of look to see how it works. So what we're going to do is we're going to, again, have the same sort of minimization term. The first term doesn't change. But now what we do is we do the following. Plus c times summation of for all I max of 0, 1 minus yi hat. And this is our new loss term. This is, in fact, let me put a box around this because it's important. Shoot, how do I do this? Yeah, this here is the soft margin SVM problem, the primal form of it. We'll revisit the dual in a little bit. But yeah, this is the soft margin SVM problem. And let's see how, in which way it generalizes the previous. So now note that, how does this work? Note that for any point where this 1 minus yi hat is less than or equal to 0, then if you feed that into this term overall will be 0. And in fact, if you have this property for all points, where all points 1 minus yi hat is less than or equal to 0, then the loss function is going to be exactly the same, in the sense that you'll only pay based on the L2 norm of the parameter vector. So that's great. But now what we're saying is that, okay, we're going to allow you to have values which are greater than 0. But if you have a value that's greater than 0, then this is paid, you pay linearly in your overall loss function based on how much you go over the line. Okay, so let me also, I didn't really address this big C sitting right here. This C is a hyperparameter, which says how much you want to, how much you pay based on these misclassifications. So let me, should I do this first? Yeah, well, we'll revisit this in a sec, I guess. But okay, let's maybe take a bit of a closer look first before we progress at this like loss function here, which is kind of corresponding to where the points lie in the space. So yeah, let me write this as follows. So first of all, there's kind of 3 cases of where of the geometric picture you had. So let's try to draw this. So let's suppose we have some sort of linear classifier, kind of as before, and let's draw the margins right here. So these are the margins. So it's going to be kind of similar in the sense that the solution is going to be the same, and that there's going to be some hyperplane which separates the which is going to try to separate the two classes. There might be some exceptions now, but there's going to be the 2 margins which are kind of sitting one away from it in this normalized version of the problem. But okay, so let's this is what we've got, and let's sort of see what it looks like in terms of the how the loss function, this thing right here, corresponds to the value based on where it appears in this picture. So let's pretend, of course, that this side is the plus side or whatever, and this side over here is the minus side. So let's take a look at the first is the easiest case. So if 1 minus yi hat is less than or equal to 0, then it's, I don't know, I'm not sure if there's a formal term for this, but like I like to call this being strongly, I personally call this strongly correctly classified. So let me just say it's on the right side of margin. So I guess let me try to introduce some new colors here, which might get a bit confusing. I hope it's going to be okay. But let's say let me just, no, I'll not use any colors, new colors. So okay, these points here and things sitting on the margin. You'll recall that this looks very similar to this picture that we had before of hard margin SVM. Everything that is on this in this category, anything that's sort of on or beyond this line, this is going to have that 1 minus yi hat is less than or equal to 0. So these ones, in the loss function, this pays a 0. It hits this max of 0, and therefore we don't pay anything for a point which lies over here. Let me kind of indicate that this is going to correspond to points which are in this sort of area from here to up to infinity. So anything that's like across this line is going to be correctly classified. Now, of course, and similarly for these blue points, which are over on this side of this margin. Good. Now, let's see the next category. The next category is when we have that, what is it? Let's write it like this. When 0 is less than or equal to yi hat is less than or equal to 1. This corresponds to, let's say this is within the margin. So that corresponds to, this case corresponds to things which are correctly classified, because remember, this if yi hat is greater than 0, that means that it's correctly classified. But it's going to be things which are not, say, strongly correctly classified, and that corresponds to points which may fall here. So these ones here are things that, yeah, they're still correctly classified, but now they're getting kind of dangerously close to this margin. So we're going to pay something for them in the loss function. In particular, if you substitute this in here, then you're not going to hit the 0, so you don't have to pay nothing, but you pay linearly depending on how far over the line they are. So that's the second case. And the third case is going to be when yi hat is less than, when it's less than 0. And this corresponds to points which are incorrectly classified. And that's a point which is over here, something which falls on the opposite side of the hyperplane. And any of these would be incorrect. And so let me just draw that in another color. Sorry, we're running out of colors, so this starts to look a little bit ugly. But anything that's here and onwards, like kind of anything that's over the line, is going to have this yi hat is going to be less than 0, and it'll be incorrectly classified. And again, you're just going to pay linearly based on how far over its correct margin is. So this is kind of the distance from this margin to how far it is in this direction. Good. So let me try to, this is kind of the geometric view of where these points lie based on this expression, 1 minus yi hat, which can be a useful visualization. Let me try to draw the picture in terms of how much loss you pay, the loss function. That is, how big is this term here going to be, the second term here, based on where they lie. So let's try to imagine you're looking down the line of this green thing. So that we're going to, I drew this as a 2D picture, but let's look at it from the right-hand side. So let me see if I can do this. So we're going to draw a coordinate axes. This is what the green line looks like if you're looking at it from the sort of 1D plane that it lives in, or from over here. And what we're going to have is, this is the x-axis. And the idea is that there is some red plane, which is right here. Let's say another thing right here. Let me draw this a bit further. Okay, so this is the idea. The loss function that we're going to have for a particular point is going to look something like this. So anything which falls is correctly classified. Let me label this. So the loss function for any point which falls over on this side of the line, then it's going to just be 0. Now, for any, and that's any point, like I said, in this blue region here. I'm just going to do this all in one color because otherwise it might get too confusing. But any point that crosses this, you pay linearly depending on how far over you are. So this is the loss function. Anything, and you can see how this kind of corresponds to the different regions we drew in this picture. That's what the loss is in terms of how much you pay for a point, depending on the value of this 1 minus this y hat. So, okay, and this function here is known as the hinge loss. And why is it called the hinge loss? Well, you can see that it looks like a door hinge, really, like the hinge right here. And yeah, this is a function of this is the loss function as a function of yi hat. Cool. So it's called the hinge loss, and it's common and important. Let's do some comparisons. Let's compare this with the 0-1 loss. Yeah, I guess let's compare this with the 0-1 loss, which is the loss which essentially says that the function is going to be 0 if we correctly classify it. So anything that's on this side is going to cost us 0, but anything on the opposite side is going to be a 1. So this is kind of the ideal thing that we're trying to learn, because ideally we just want to find any sort of hyperplane which will pay 0 for things on this side and 1 for things which are on the incorrectly classified on the opposite side. So what we're really trying to optimize is this function here, where it's 0 here and then 1 for everything here. But instead, we optimize this hinge loss because of the fact that this is not very easy to optimize because of reasons we'll talk about a bit later, but essentially you can't get a derivative because it's going to be a constant derivative for all portions. So it's not going to give you any information. So this orange one here, let me just mark this with blue. This orange one here, this is the 0-1 loss, which is what we're really trying to optimize. And let me just compare it with one last thing. I'm sorry, there's not enough colors here, but a last thing, which is the perceptron loss. Now, the idea of the perceptron loss was that when we're doing this, we pay 0 for anything, again, which is correctly classified. So anything here. And then on the right-hand side, sorry, if anything's incorrectly classified, we essentially have an infinite cost. So I'll draw it as high as I can, but it really should be like, I'll just label this as infinity. So this perceptron, you can see, is kind of related to both the 0-1 loss and the hinge loss. It's much higher because it upper bounds both of them. At least on this region, I guess here. Sorry, both of these are important because they upper bound the 0-1 loss, but you can see that this kind of tries to upper bound in a different way compared to the hinge loss. So yeah, hopefully that's clear, and this is a picture of 3 different loss functions and how they relate to each other, but hinge loss is kind of the most interesting one compared to the other 2. Good. What do I want to say next? I want to talk about, the last thing I want to talk about is how else is this a generalization of the hard margin SVM. So let me just point out the fact that what happens if you take C to its extremes? C, like I said, is just some hyperparameter. It's going to be a hyperparameter similar to lambda when we were doing, say, regression, ridge regression, or lasso. Well, in this case, C is a hyperparameter which says how much we pay depending on the points versus how much we pay depending on the magnitude of the norm of the parameter vector. So let's look at some extremes. Suppose we set C equal to 0. If we set C equal to 0, then this term over here would just disappear. It would be completely gone. And all we're trying to do is optimize minimum, you minimize the L2 norm of W. So it'll ignore the data, and it will, it'll ignore the data and essentially just try to optimize this norm, which will set it to 0, I guess. So it'll be very uninteresting. So that's if you set C equal to 0. On the other end of the spectrum, if you set C to be equal to infinity, then we're not going to care at all about this, because any sort of violation of this would be, well, okay, it's not the exact same thing, but essentially we'll place almost no importance on this, and essentially it'll reduce to the hard margin SVM, in the sense that if there is a solution which is linearly separable, then you have to find it. And the reason is because that you pay as far as you go over the line. So therefore, if you go over the line even a little bit, you'll pay an infinite amount if C is set equal to infinity. And then, you'd really want to prefer things which pay the 0 cost. So let me just sort of summarize this discussion and say that C equals 0 means you ignore data, whereas C equals infinity means you only care about data. And in fact, this reduces to the hard margin SVM if, and it's kind of like the hard margin SVM when a solution exists. But if there's no hard margin SVM solution, then it's kind of a little bit different. We'll see. But don't worry too much about these extreme cases. I just want to show that it kind of can be related. Okay, so let's talk about the dual and in fact rederive it for this case. This is going to be a similar calculation to how we did it last time, but I'm not going to explain all the steps as in depth. There's going to be a few kind of new tricks that we have to do here though. So let's start first of all with the objective function. So recall why we derive the dual. The reason we derive the dual is because it has some nice interpretations and may be easier to interpret in some ways. It might be easier to optimize, and also it has some nice interpretations. So this is our optimization problem. And in fact, like I said, this is going to be the primal as opposed to the dual solution, or the dual problem. So what we're going to do is, first of all, this might seem a little bit backwards, but the thing is that this is kind of a difficult thing to deal with. So what we're going to do, like the fact that we have this max here. So what we are going to do is we're going to define something which is called a slack variable. And well, let me rewrite this into an equivalent form. So we're going to have minimum WB 1/2 norm 2 squared plus C times summation. And now I'm going to introduce what are known as slack variables, C times gamma I. So just one crucial thing I want to mention, these gamma I's are not the same gamma I's that we used in the previous lecture where we were talking about the margin. I just used this because it's a convenient symbol, but it's kind of related. But anyway, these are just going to be, they're not the exact same thing, so don't get that confused. But anyway, these are going to be slack variables. And what we're going to do is we're going to say we have this optimization problem such that for all I, we have that max of 0, 1 minus yi hat is less than or equal to gamma I. Yeah. So this is essentially an equivalent way of writing this, just saying kind of similar to how we use margin. So like, yeah, it essentially says that all of these variables, all of these things are going to be less than or equal to gamma. So this is going to be more convenient for reasons that we'll see and get into. The reason is, okay, this is not where we finish, in the sense that what we can do is we can also expand this to write this as W comma B 1/2 WL2 squared plus C summation of gamma I. And the next thing we're going to do is we're going to break this up into two constraints, because if it says that max of 0 in this term are less than or equal to gamma I, then they're both less than or equal to gamma I. So such that for all I, we have the following constraint: 0 is less than or equal to gamma I. And we also have that 1 minus yi hat is less than or equal to gamma I. Good. So this is an equivalent way of writing the problem. And now what we're going to do is finally, at long last, we're going to take the Lagrangian dual. So how do we do this? Remember, we just take these constraints here, rearrange them a little bit, and write them in the summed into the objective function. So let's do this. So this can be written as equal to min over WB. And now we're going to have max over, this time we're going to have, since we have two types of constraints, we're going to have two types of dual variables. Alpha kind of takes the same role as before, but now we also have beta, and we want these both to be non-negative. And we're going to have the following: 1/2 W2 squared plus summation of C. What's the... Yeah, let me write it like this: summation over I of C gamma I plus alpha I 1 minus yi. And yeah, this is one big summation containing all of this. And yeah, all we did was move these appropriately, multiply them by dual variables, and put them in the objective function. Good. So the next thing we're going to do is we are going to swap these two, again, using strong duality. Yeah, let's see how we can do this quickly rather than rewriting this whole thing. So we'll just copy this and swap these. So strong duality allows us to do this. Recall that but I'm not going to say really why. And now, based on this fact that we have a minimization problem here, again, we can just take the derivatives and set them equal to 0. So what do we get here? If we take the derivative of this term with respect to... Oh, let me mention, sorry, there's one thing one thing I neglected here. Now we have an additional, once we did this sort of slack variable thing, we now have an additional variable which comes in right here. So we have to optimize also over gamma. So similarly here, gamma. Yeah, we're trying to minimize with gamma in mind. So now let's take the derivative of this expression with respect to each of these different variables. So partial with respect to W is actually identical to before, in the sense that we have this term and we have this term here. And if you do it exactly like we did last lecture, we have W minus alpha I yi xi is equal to 0. Similarly, taking the partial with respect to B is going to be very similar to before. And in fact, we get the exact same expression. Yeah, an easy way to see this, in fact, is just by perhaps, if you expand this out a little bit and draw all the gammas to the right-hand side, these are going to disappear when you take the partial with respect to W and B. So it's exactly the same if you ignore the gammas as before. So this just becomes equals minus summation of alpha I yi, which is equal to 0. And the final thing is going to be this partial with respect to gamma I, which is the trickiest part, perhaps. Actually, no, it's not too tricky, because if we'll just look at this, it's actually very easy. I don't know why I said it's tricky, because I mean, there's a single variable derivative. So if you look at gamma I, then you have the C here, so it'll be a C, and then plus alpha I, or sorry, minus alpha I, because we have minus gamma times alpha I here, and then we have minus beta I. And this is also going to be equal to 0. So, okay, this is nice because we've got all of these derivatives here. Now let's do the exact same thing as before and just plug them into this expression to try to get rid of this min. We just want to make it into a single maximization problem. And I'm going to skip over some of the steps because we already did them last time. For example, these are the exact same things as we had before. So I'm going to try to skip over some of those ones just to avoid duplicating work. You can check them yourself. But let's perhaps take a look at the most important parts, or in terms of the parts which actually change. And those will be, you know what, let's just do it fully just because it's simple enough, but I'll do them a bit quicker than I did last time. So first of all, let's just take a look at the first term. This term, I'm just going to first convert this term, like simplify this term, and then I'm going to simplify this term. So what we can do here is essentially plug in this first derivative right here, and this will tell us that this can be written as, just plugging it in as a dot product or whatever, be written as summation over I, summation over j, alpha I, alpha j, yi, yj, and then inner product of xi, xj. So this should look familiar in the sense that this is exactly what we had from the last lecture when we took the first term. Okay, but let's take a look at the terms which don't involve this. Let's actually go to that first. So let's take a look at the summation of what is it? Minus alpha I yi times yi hat. So this is the terms. So we're just taking out this and this. We're not going to touch the rest of them for now. So those terms, this is going to be equal. So let's expand out this yi hat. So this equals to minus summation alpha I yi times inner product of w xi plus b. Well, as you might recall, so there's two things here. This can be rewritten as minus times summation of alpha I yi inner product of w comma xi plus summation of alpha I yi times b. Sorry, this is getting a bit cramped here. Let me write it on this next line, actually. Something like this. Now, recall that due to this condition, this term will go to 0. And this term, doing the same type of substitution, which we also did in the last lecture, this term can be rewritten as basically minus 1/2, or minus the same term here. So kind of skipping ahead, this term goes to 0, and replacing this with minus 1 times this, then we have that this becomes minus summation over I, summation over j, alpha I, alpha j, yi, yj, inner product of xi, xj. So make sure you understand why this follows. I did it in depth in the last lecture, but you can hopefully either look at that or derive it yourself right here. So let's see, that's almost all of the terms done, or those are kind of the trickier terms, I'd say, to deal with. So now let's just deal with the remainder terms. We still have, so we've dealt with this. We've sort of expanded it and simplified it. We've dealt with this term. So the ones that remain are this one, this one, this one, and this one. So scribbled all over there, but let me just write it here. The ones that we still have to deal with are summation over I c times gamma I plus alpha I minus alpha I gamma I minus beta I times gamma I. So hopefully convince yourself that these are the terms which are not contained either here or here. And let's just do some substitutions to simplify this. So one thing we're going to notice is the fact that this right here can be rewritten as C is equal to alpha I plus beta I. And that's nice because that allows us to eliminate this. And in fact, that cancels out this exactly. So let's just do that. This becomes alpha I plus beta I times gamma I plus alpha I minus alpha I gamma I minus beta I gamma I. And like I said, this cancels out with this, and we're just left with is equal to summation over alpha I. And okay, so what have we done? Well, I did a bunch of expansions, and this is kind of a mess now. But let's take a look at what we did. So we took this and we took all of these terms here and we simplified them to basically eliminate the dependence on W, B, and gamma. We got rid of all the primal variables, and now we've got it only in terms of the dual variables. So what I'm going to do is I'm going to take these different terms, which I simplified each of these two, and substitute it in, and we'll see what we get. We need another page here. So if we do all this simplification, what we have is the optimization problem as follows. We have a max over alpha and beta. In fact, let me just negate this and turn this to a minimization problem, just because that's what you see more often. And it's perhaps, it's the final form that we're going to go for. So alpha I beta is greater than 0. So again, this is just negating things. And then the inner product of xi and xj. So this is what we have here, and then minus the summation of over I of alpha I. That's the simplified form of this expression. And remember that we still need the constraints which we derived here, which are in fact the fact that what do we still have? We still need that two things. We need this constraint is kind of used up because now W doesn't appear anywhere else, but we still need this one as before, and we need now also this one as well. So these are the constraints that we have, such that summation of alpha I yi is equal to 0, and we also have that Ci equals alpha I plus beta I, or sorry, not Ci, because it's just one C. And we have this for all I. So these are, let's take a look at this and like maybe recap a bit what we have. So we have this optimization problem where we have these two constraints. And in fact, you might realize if you were paying close attention that this is very, very close to what we have for the soft margin SVM or hard margin SVM. In particular, this objective function is exactly the same. The only difference is the fact that we have this beta greater than 0 here, this new beta here, which is weird because this beta doesn't actually appear anywhere in this objective function. But the thing is, it kind of implicitly appears here in terms of its relationship to alpha, and alphas do appear here. So like this constraint and this, and everything is red. These are the diffs versus the soft margin versus hard margin. So yeah, these are the only differences, and it turns out there's a way to simplify this a little bit. it feels weird, right? Because I said this beta doesn't appear here, it only appears implicitly. Well, let me show you how to simplify this so that it actually looks very, very close to the hard margin SVM. So all we have to do is notice that here, that B, or beta I, we're just going to do a substitution. What we know is that beta I is equal to C minus alpha I. And we know that beta I has to be greater than or equal to 0. So we can say that C minus alpha I is going to be greater than 0. And so this equivalently, this is the only way that beta I is used to derive this constraint. So that equivalently means that C is greater than or equal to alpha I, entry-wise. And with this relationship, that completely removes the dependence on beta in every way. So let me finally write down what the SVM, the soft SVM dual is. So it's essentially exactly this. Except for the fact that what we're going to do now is, because we have managed to get rid of this beta, we now just have alpha is greater than or equal to 0. And the new thing is, right, we said that C is greater than or equal to alpha. So this is the one change. So C is greater than or equal to alpha. So now this is rather nice because it shows exactly how close these two different problems are. Remember, so this is the dual version of the problem. And let's take a look at before, when we looked at before the hard versus soft. Well, they look kind of a lot different because we have these hard constraints here and stuff like that. And then we have to put them in the loss function. It's kind of a bit awkward and they look very different, or reasonably different. But when you look at the dual version of the problem, they looked almost identical. In particular, you just add or remove this C here, and then it becomes either the soft or the hard margin SVM problem. So that's really nice, the fact that just adding or removing this will be key. And in fact, if you set C equal to infinity, then you can see that's exactly the connection we made before, where if C equals infinity, then it just becomes a hard margin SVM. Good. So this is all there is to it. That is the dual soft SVM. Let's comment on this, and in fact, comment a bit more about these. As before, let's comment on the support vectors. That is the alpha I, which points have alpha I greater than or equal to 0. But first of all, let me just again remind you, this is still hinting at stuff we'll talk about during the next lecture. The fact that we actually take the inner product of xi and xj, and we don't actually require the values of xi and xj. This is going to be very important for certain feature operations we're going to do on this. So in some sense, for certain problems, the primal problem will not even be solvable, whereas the dual problem will be solvable because it's only represented, it only requires these xi's based on their inner products. Okay, so if you remember before, let's draw the picture we had from last time where we were talking about the support vectors and see what we can say now in this other case. So remember the picture we had before where these lines, something like that. It doesn't have to be perfect. And we had some points here, 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 and so on. And then minus points over here. Things on the margin as well as things beyond the margin. And so what we said before in the hard margin case, everything here that's beyond this margin, that will have an alpha I equal to 0, whereas things on this margin, the alpha i's may be 0 or they may be greater than 0. And again, why is this useful? This is useful because it lets us, given a solution to the dual problem, we can compute the primal solution, that is the actual parameter vector, which is what we're generally looking for. We can compute it as a linear combination of alpha I times yi xi. So the idea is if we want to find a solution, we really if we want to convert a solution of these alpha i's into something for the primal form, which is finding this parameter vector, then we need to know what the alpha i's are for each point. And so understanding which ones are non-zero is important. So therefore, computing the alpha i's, yeah. So the things over here across this margin are going to have alpha I equal to 0 every time. So they're not going to factor into the summation. But things on this margin may or may not have alpha i's greater than 0. And those, again, as we call them, anything with a non-zero alpha I is a support vector. So let me write that here. Alpha I greater than 0 implies that it's a support vector. That x is a support vector. Xi is a support vector. Now, so that's for a hard margin SVM. Now, what about for soft margin SVM? Now, when we have points which are allowed to go in here, well, let's see what happens. Well, okay, first of all, let's recall some of the conditions that we used. Again, we used the complementary slackness of the KKT condition and out of the KKT conditions. And that essentially says that these things which we had as constraints here that we moved into the objective function, those all have to be satisfied. Those all have to be equal to 0. So this term has to be equal to 0 for all n, for all I, and this has to be equal to 0 for all I. So let me just sort of summarize that here. So that means that for all I, we have that alpha I times 1 minus yi hat minus gamma I is equal to 0. And we also have that beta I times gamma I is equal to 0. These are the complementary slackness conditions. Furthermore, remember that we had the substitution that we said that beta I, we eliminated beta I, and this is just equal to C minus alpha I. So then we can have C minus alpha I times gamma I is equal to 0. So these two right here are going to be the sort of key complementary slackness things that we are going to use, this one and this one. And okay, let's try to see what this tells us about what this tells us about the alpha i's for various points. In particular, I want to discover more about our support vectors. That is, suppose that alpha I is greater than 0. Well, what does that mean? That means this term right here is equal to 0. Then this implies that 1 minus yi hat minus gamma I is equal to 0. Just because this product has to be 0, so one of the two has to be 0. So what does this mean? Well, there's a few different cases here. First of all, one case is say like gamma I is equal to 0. And recall, we talked about the different cases. If gamma I is equal to 0, then this rest of the term will be equal, 1 minus yi hat will be equal to 0. And that corresponds to points which are on this margin. So this is talking about points, say, like which lie on here. And what we can say about these points, if they, essentially for things on the margin, because we have that alpha I is between 0 and C, for these points here, we know that we have 0 is less than or equal to alpha I is less than or equal to C. Any of them is possible. Whereas, recall, for the same reason as before, as we talked about last time, if we have anything beyond it, then this term will not be 0. So therefore, the alpha i's have to be 0. So for this term, for a point like this, alpha I is equal to 0. But for things like this, which lie on this margin, like exactly on the margin, then the value attached to it could either be 0 or it could all be between 0 and C. It may be non-zero, it may be 0. So then this implies that, but okay, if we're already assuming that alpha I is greater than 0, then this implies that 0 is less than or equal to alpha I and less than or equal to C. Okay, and for the other case, say gamma I is, remember these are non-negative random variables or variables. These are, say it's going to be greater than 0, so it's either equal to 0 or greater than 0. In this case where it's greater than 0, then by this other condition, we have that c minus alpha I has to be 0. And this therefore implies that alpha I is equal to c. So that means for any point which lies between or on the other side of the margin, so let me draw points here, 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 for say all of these, for any of these points that we have which are sort of on the other side, alpha I is equal to c. So it's exactly c, then there's no other choice, because otherwise these conditions won't be solved. So yeah, this is kind of cool how, again, based on the geometric perspective that we obtain from this dual solution, we can see what the alpha i's, how they're going to be. Things which are strongly correctly classified way on the other side of this. So things which are strictly across the margin, though they're always going to be 0. Anything which lies on the margin may be 0, or it may have a non-zero value anywhere between 0 and c. Things which are within the margin or on the other side are going to be equal to c. So this tells us which points have the potential to be support vectors. And this kind of, I think it's cool. There's other things you can do by also like trying to say, okay, suppose alpha I is equal to some value, then where could it be? There's different deductions you can make about where a point lies depending on various values of alphas and gammas and stuff. But I just want to show you basically which points are going to factor into this expression for W, and which ones may have potential to be support vectors, or anything which are either which have non-zero loss or lie on the margin for this classification problem. Yeah, so that's the support vectors, and that's all I want to say about. Okay, I was going to do it over here. Let's I guess skip some of this. But this is not too important. We'll not do this. Yeah, so hopefully the concept of support vectors makes sense to you, and which points may or may not be support vectors, because this is kind of, I think, a very beautiful geometric picture. Cool. As a last thing I want to talk about in this lecture is optimization. Remember last time I said we're not going to solve hard margin SVM just because of the fact that hard margin SVM is a simpler problem than soft margin, which is more general. So let's talk about how we optimize soft margin SVM. Well, remember, let's just write out the hinge loss. The hinge loss at a given point WB with respect to a point XY is equal to max of 0, 1 minus y times something like this. And the loss function is equal to, the overall loss for a data set is going to be equal to, we can write it as follows. Okay, C over N. We're going to have a normalization in here. This is a bit different from what we've studied so far, but I just want to write it this way because this may be more common when you're actually doing the optimization. The other way was, I didn't want to really get the N involved, so this is perhaps, yeah, let me write it like this. Plus 1/2 times the L2 norm of the W. So this is the loss function when we're trying to optimize a soft margin SVM. And again, this might look very similar to you in the sense that this looks like an L2 regularized problem, which exactly it is. It's very similar to ridge regression, where we could write in the exact same form, though instead of using the hinge loss, we would be using the L2 norm squared. Would be using the squared loss rather than the hinge loss. Another comment I'll make is the fact that it might seem a bit different because before we put like a lambda here and we just had a 1 here. Well, yeah, this is just sort of a difference in where the regularization parameter goes sometimes. So you can also represent SVMs as putting a 1 here and a lambda here, and it'll kind of be the same thing. But this perspective we use so far was more convenient in terms of deriving the dual and all that. But just, yeah, note that another representation you'll see sometimes has a lambda here instead of a c over here. But okay, how do you optimize this? Well, you just take the derivative and you do gradient descent. So this is often optimized. I mean, there's many ways to optimize. Some involve looking at the duals and fancy things, but a valid optimization method is gradient descent. And it's very simple to optimize this, because all you have to do is you take the derivative with respect to, I mean, w. I'll take the partial with respect to w, and you can do the same for b if you want. But the partial of w with respect to w is going to be equal to w, which is just this term, plus c over n times the summation of some delta i's. Now, why, like, where this delta I is going to be either equal to 0 if I'll draw a picture in a sec, so we'll see. And minus now, this might seem a bit odd, but let me explain a bit. So let's draw the picture we had earlier. This is the picture of the hinge loss we had. Let me draw this in a different color, say orange. We had a picture something like this. So what this says is, what is the derivative of this term? Well, it's going to be, on this part, it's going to be 0. On this sort of flat part here, that's a 0 derivative. And here, it's going to be basically -1, which we're going to sort of rescale by the terms inside, because it's going to be using chain rule. But yeah, the derivative here is going to be -1. The thing is, you might, keen-eyed watchers might have noticed that actually we have some ambiguity. What happens if you have this is equal to 0? Well, that corresponds exactly to this point right here, which is the hinge itself. And at that point, the function is not differentiable. And so what you have to do with this type of thing is take any sort of subgradient, where essentially it says that either of the two cases would kind of work for you. So it's not quite differentiable, but it's differentiable almost everywhere. So it generally works well enough. So that is how you take the gradient. Yeah, and that's kind of how optimization works for this problem. Just use gradient descent, and that's simple enough. There's other, like I said, fancier methods. You can additionally, if you want, do gradient descent for the dual problem. The trickier part, perhaps, for the dual problem is it's not as easily writable like this, in the sense that, let's go back up to the dual version of the problem right here. Yeah, so when this dual version of the problem, you can take some derivatives. It's a little bit hairier, but you can always do it, and then optimize. The thing is that we have some constraints, which is basically, say, C has to be an upper bound on the alpha i's, and that we also have to have this summation alpha I y equal to 0. So these constraints we have. But the thing is, when you're doing optimization with these constraints, and what you can do is something called projected gradient descent. I might include this, I might talk about this in a later lecture or something in a bit more detail, but the idea is the following. What you do is you run gradient descent, where you recall each step of gradient descent, you take steps which get you closer and closer following the direction of the gradient. But the idea here, let me actually draw a picture of what I mean by projected gradient descent. Yeah. Just to get you some idea, because this is a common thing that you'll see, so I don't want you to be scared if you see it in the future. It's basically trying to convey the following thing. So we have some set of possible feasible solutions, say something like this, and you can think that just to sort of relate it to our problem before, this is a set of possible solutions where C is greater than or equal to alpha is greater than or equal to, let's just say alpha is greater than or equal to 0, and that we also have summation of alpha I yi is equal to 0. So this is the possible set of feasible solutions. And what we do when we do gradient descent is we start at some point, and we take the gradient, and then we follow it in one step. But the thing is, that step that we take might take us out of the set of feasible solutions. So maybe we find that the right way is over here, but that actually takes us, let me draw it the opposite way actually. Maybe it's in this direction, but actually that takes us out of the possible feasible solutions. So we go here, but then find out that this is not valid. So what we do before doing the next step of gradient descent is we actually just project it on back into the set. So we find the closest point within the set and we go back there. So let me kind of label these in some way. This is the right here, this is the gradient step. And this right here is the projection. And so one step of projected gradient descent would be basically a combination of these two things. And then from there, we can do, say, the next step, which I don't know, maybe it's something like here, and it takes it over here. And then we do the projection back in to here. And then eventually, I don't know, at some point we find that the solution is over here. But that's essentially all that projected gradient descent is. You have some set of feasible solutions, and you just alternate between gradient steps and projection steps to get back into the set. Yep, so that's everything that we wanted to talk about for support vector machines. They're a very important part of of machine learning. They can be a little bit more mathematical than some of the stuff we've talked about so far in this class, but I think there's a lot of important topics here, so I hope this makes sense.